Hello, and welcome to this lesson on linear versus nonlinear functions. Our goal of this lesson is to be able to determine if the function we're looking at is linear or not. That's it. So far, all the discussion we've had on functions has been on linear functions. Everything has been could be written in slope-intercept form. That's that y equals mx plus b. So now our job is to figure out if the thing we're looking at is a non-linear function. Some of these are very easy, some are, well, none of them are really actually that hard. Some just take a little bit more work than others. So the central question says, how do I determine if a function is linear or nonlinear? Pretty straightforward. Did you know that there are many situations when something is not increasing or decreasing at a constant rate? That phrase, constant rate, for us, means linear. Straight line, the rate, the slope is not changing. In these situations, a nonlinear function can sometimes be used. So an object's height after being let go, it doesn't actually go, height over time, it doesn't go like this. It's not a straight line. It's actually more of a parabola. It looks kind of like this, where the object, when you first let it go, it falls slowly at first, but it gets faster and faster and faster as gravity's pulling it down. Your grade over a year might be nonlinear. It's probably not a straight line. Your bank account over time, the temperature over the course of a day or a month or a year is definitely nonlinear. Okay, so a linear function is a function whose graph forms a straight line. The slope remains constant. That's that constant rate we were talking about. We could also add here that this will always be written in the form y equals mx plus b, or could be rewritten in this form, even like 3x plus 2y equals 9. This is linear, even though it doesn't look like this, because we could rewrite this in slope-intercept form. That would be y equals negative 3 over 2x plus 4.5. So I can do it, I can make it slope-intercept form, which means it is linear. If I cannot do this, if it's impossible, then you're looking at something that is a nonlinear function. So a nonlinear function is a function that, when graphed, does not form a straight line. You probably could have guessed that. It can be increasing or decreasing, or both increasing and decreasing. So increasing function could be like that. It's going up everywhere, but it's not a straight line. Decreasing, I showed one of those a second ago. Or it could be increasing and decreasing. It can go like that. That could be a function, just a curvy function. Okay? So, each relation shown is a function. I'm telling you it is. Is the function linear or non-linear? If it is linear, tell me the slope and the y-intercept. All right, so first one, is this linear or nonlinear? Can we write this in slope-intercept form? Can it be written like this? Yes, it can. This is linear. If I would subtract 2x on both sides, I can get the y by itself, and this is perfect slope-intercept form. So linear? Yes, it is. Now, it said if it was linear, find the slope and the y-intercept. So slope, and how about this? Instead of writing out slope and y-intercept, I'm going to put m, because that's my slope variable, b, because that's my y-intercept variable. My slope is negative 2, my intercept is negative 15. Done. That is linear. It has a slope of negative 2, it has a y-intercept of negative 15. Letter B. Is this linear? No, clearly it's not linear because it's curvy. It's not a straight line. But also, more importantly, the slope is different at different places. If I find the slope from here to here, we get that slope. If I would copy and paste that, copy, paste, I'm not going to find the same slope here, or here, or here, or here, or here. I mean, the slope is different literally everywhere. The slope here oops, would look like this. Whoa, that was unexpected. Would look like that. The slope from these 2 points would be here. The slope from those 2 points would be there. So the slope is different everywhere. That's another reason why this is nonlinear. The slope is different. The slope is not the same everywhere. Which actually is how we're going to do problem letter C. So looking at letter C, I want to know if this is linear. Now, you've got options. As you've seen quite a bit, we actually have options in math. You're not used to this. You could, right now, get a piece of graph paper and graph it and see if it's a straight line. You could, with your graphing calculator, you could go in here to stat and you can edit a list, and this is the list we had before, and you can put in -3 and, oh man, what did we mess up? I wanted to do it. There, list, oops, stat. We're gonna clear. Can we? We're gonna clear list. And say which list? Well, we want list 1. Enter. Done. And then we're gonna clear list. I'm trying to empty them out from the last time we used them. And now I'm gonna clear list 2. And now if I go back in here, oh man, whatever. I'll fix it. So -3, boom. -2, boom. 0, 1, 5. -8 should work. There we go. -5, 1, 4, 16. This is one of the benefits of having a graphing calculator. Now, we could go and say we want to graph the stat plot. Remember that? Second, this y equals. My plot 1 is on. I can double check the settings of it. It's on. It's graphing a scatter plot. All that junk looks good. So if I hit graph, it looks like a straight line. But that's not good enough. You can't say, oh, it looks like. I mean, if 1 point was off by 1 measurement, we probably wouldn't be able to tell here. In fact, I don't even see all 5 points. I've got 5 here. I only see 4 there. So it's okay. It's enough to go, man, that's pretty darn close to a straight line. Desmos would be the same deal. Okay. The most accurate way of telling whether this is linear or not is to find the slope at 2 different places and see if the slope is the same. I'm going to find the slope right here. x1, y1, x2, y2. I'm using the formula m equals y2 minus y1 over x2 minus x1. Now, I'm shortcutting a lot of this stuff in my head because I know a lot of this by now. So 4 minus 1, that's y2 minus y1 over x2 minus x1 equals a slope of 3 over 1, which is 3. So right there between these 2 points, 0, 1 and 1, 4, there is a slope of 3. If I find the slope again somewhere else in here, the slope had better be the same. To avoid all of those negatives up top, I'm going to then find the slope right here. So I'm going to use, this is my x1 and y1. This is my x2 and y2. So I'm going to use y2 minus y1 over x2 minus x1, giving me 12 over 4, which equals 3. I got the same slope. Same slope means linear. If the slope is the same everywhere, it's a straight line. Now, you really only have to check twice. I'm going to do it a third time just for safe measurements. So x1, y1, x2, y2, negative y2 minus y1 over x2 minus x1. You see why I skipped those first 2 points, all those negatives. -5 minus -8 is a positive 3. -2 minus -3 is a positive 1. And look at that. It's the same slope. Which means this is linear, 100% guaranteed. It looked like it when we graphed the points. Now we can show it. We can prove it because the slope is the same everywhere. Okay, I only had to check twice. If I check 2 times and the slope is different at both places, you're looking at a nonlinear function. With that in mind, I would like you to do letter D right now. So we have space down here if you need to do the work, but I want you to tell me, is this function for letter D linear or nonlinear? Go ahead and pause the video, do it right now. When you're ready to continue, hit play, and we'll go through it together. All right. Oh, I even forgot to say, this one is linear. Oh, man. And then it said if it was linear, we're supposed to find the slope and the y-intercept. I guess we didn't do that. So slope is 3. We found that there. Y-intercept is 1. We found that right here because the y-intercept happens when the x value is 0. All right, back to the problem we were supposed to be doing, letter D. Is this linear or nonlinear? You should have found this to be nonlinear. Now, I can tell by looking at the table it's nonlinear, but if I start finding slopes at places, y2 minus y1 over x2 minus x1 gives me a slope of negative 12 over positive 2, which is a slope of negative 6. If I find the slope somewhere else, y2 minus y1 over x2 minus x1, by the way, x1, y1, x2, y2, in case you're curious where the numbers came from, that gives me 7 over 2, which is, well, doesn't simplify, so 7 over 2. Not the same. Negative slope, positive slope. Not the same. Nonlinear. Okay? You could have graphed this. If you would have graphed these points on a graphing calculator, you would have seen very, very quickly and clearly that it is not in a straight line. It is very bumpy all over the place. You could have also done this in something like Desmos. I keep going over to that tool. Oh man, why did I do that? We can do this and make our life a little bit easier. So I don't have to like flip back and forth between screens. I can add a table in here. I can put in, it's so super tiny, -4 and -2 and 0 and 3 and 5 and scrolling up 12 and 0 and -4 and 5. Finally, that's a 21. All right, and then we'll make the Desmos side a little bigger. Hey, look at that. It's not linear. They're kind of all over the place. Okay, so that works. Graphing by hand would have clearly shown that as well, but finding the slope twice like we did is kind of the preferred method. Okay, but I'm giving you choices. I'm letting you see, but don't rely on the graphing calculator too much. Don't rely on Desmos too much because, well, you can't use Desmos on a test. Graphing calculator you can. That's the advantage of having the graphing calculator. You can use it on a test. That's an okay tool, but Desmos, unfortunately, you're not allowed to use that on a test. So you're not allowed to use on the PSSAs either. Letter E. Now, we've never seen anything like this before. Check this out. This is an equation. It looks like we could put this in slope-intercept form. The only issue I have is this this exponent here. If I try to make this look like slope-intercept form, so I add 4x cubed to both sides, I get 2y equals 4x cubed plus 16. I divide by 2 everywhere. We get y equals 2x cubed plus 8. Looks like slope-intercept form, but it's not. I'll do graphing calculator first, and then I'll do Desmos. So y equals, go down the first one, oopsie. So y equals, it already has y equals there for us. So y equals 2, this is our variable button, 2x to the third power, that's caret 3, 2x to the third power, get out of the exponent plus 8, and I bet you right now if we hit graph, it's going to show us those points still. See, that's because we still have the, we still have the stat plot on. So if I hit second y equals, I can turn off that this. I don't need it. And now if I go back and graph, it'll show it again. There it is. And we can see that is not a straight line. It is a curvy. This exponent is making it curvy. If we go into, we don't need U anymore. If we go into Desmos and we pull up, got rid of U, y equals 2x to the third power plus 8. We can kind of get a little bit better view of it in Desmos. The graphing calculator is sometimes a little wonky to use. Oops. So we can see here very clearly that it is a curvy. In fact, it will always be a curvy as long as this thing up here is not a 1. So right now, here, let's make Desmos the full screen. I don't need the thing. We're playing, we're discussing. All right, so straight line M is 1, which it always is. Remember how way back we were talking about exponents. If you don't see an exponent, there's always one of them. Now, if I change this, I'm gonna make the step a whole number. We don't. Ooh, no. We don't need to move like partial steps. All right. So now, if I go from 1 to 2, 3, 4, 5, 6, 7, 8, 9, 10. Can I see what's happening? It's not a straight line. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Straight line. Negative, oh, sorry, 0. I guess 0 is a straight line too. Negative 1, 2, 3, 4, 5, 6, 7, 8. Oopsie. 6, 7, 8, 9. So it will always be a curvy if your exponent on the variable is not 1. So we go back over to notability. That makes this 100% guaranteed nonlinear. Okay? If there's an exponent on a variable, it is nonlinear. Letter F. Well, that's very clearly linear. I can see it from here. It is a straight line, and I can find my slope that we're supposed to find. I can find my y-intercept we're supposed to find by looking at the pretty picture. The y-intercept is positive 1 right there. My slope is down 1 over 3, down 1 over 3, down 1 over 3. All right, now we've gone through a bunch together. You did one. Now it's time for you to do a bunch more. We got to get some practice in us. So if you could please pause the video right now. Try these two on your own. When you're ready to continue or you get stuck, hit play and we'll go through them together. All right, so letter G. Hopefully you said is nonlinear. It is a very curvy line. It is not a straight line. Linear means line, straight line. Letter H appears to be linear. I think it's linear, but I'm going to double check. This, actually, I'm going to find the slope here, and then I'm going to find the slope here. I'm going to use the slope method as opposed to the graphing method. So y2 minus y1 over x2 minus x1 gives me 10 over 2. y2 minus y1 over x2 minus x1 gives me 10 over 2. They have the same slope. So if it's linear, we were supposed to find the slope and the y-intercept. If you didn't do that yet, could you please pause the video and do them real quick? Find the slope and the y-intercept. If you did do it, you should have found the slope is 5. That is 10 over 2 simplified is 5. And the y-intercept is negative 3. That is right here, because that's when my x value is 0. Letter I. Pause the video. find out if that is linear or not. And when you're ready to continue, hit play. We'll go through it together. All right, letter I, you should have found this to be linear, because you can make this y equals. If you subtract 2x on both sides, you get y equals 1x minus 5. That is slope-intercept form. There are no weird exponents in there. So this becomes, well, my slope is 1. My y-intercept is -5. Applications. An airplane flies directly from Harrisburg to Baltimore. Mark writes a function to determine the height of the airplane as it flies. Is this function linear or non-linear? Use words, numbers, or models to justify your answer. Okay, so if you're talking about the direction the airplane goes, and you go, oh, it goes from Harrisburg to Baltimore, then that looks like a straight line. You go, oh, that's linear. But that's not what the question's asking. He writes a function to determine the height of the airplane as it flies. So the height of the airplane from Harrisburg to Baltimore is going to do this. It's going to take off. It's going to fly flat for a while. It's going to land. That is non-linear. And this beautiful picture here is my model. That's a perfectly good reasoning on why. In fact, oh no. Wing. Wing. And then you can take him and you can even copy and paste it and then turn it. Yeah. And paste him and turn him. Yeah. I think he's getting bigger each one. There you go. So we can see the airplane the height of the airplane over time is not linear. Okay. Letter B, this one's for you. Isabella sketches a function that passes through these 3 points. Isabella believes this is a linear function. Is she correct? Explain your reasoning. Okay. So this one's for you. If you could please pause the video. Determine right now, is this function that goes through these 3 points, is it linear or non-linear? And have some work or reasoning behind it. Pause the video, hit play when you're ready to continue. Okay. So, I mean, you got methods. You can graph them with Desmos or your graphing calculator. You could, which is the way that I'm going to do this, I'm going to actually just find the slope here and find the slope here and go from there. I personally like the slope method because I don't think the graphing method is too accurate. Even though 3 points might look like they're in a straight line, they could very easily be off by a teensy bit. But slope is never wrong. So I'm going to do my m equals y2 minus y1 over x2 minus x1. And that would be x1, y1, x2, y2. 4 minus -3 over 2 minus 5 gives me 7 over -3. Okay, interesting slope, but that's what it is. From the second set of points, I'm going to change color here so we don't get ourselves confused. From these 2 points, I'm going to use x1, y1, x2, y2 being y2 minus y1 over x2 minus x1 gives us -21 over 9. And that simplifies down to -7 over 3. Would you look at that? -21 fraction 9 simp equals we're changing into a mixed number for an improper fraction, so it's -7/3. So is it a linear function? Yes, linear. Explain your reasoning. They have the same slope, or the slope is the same everywhere. I guess is a better way of saying it. The slope is the same everywhere. You could also say the slope is constant, which also works because the fact that it's constant means it's the same everywhere, and something with a constant slope, a function with a constant slope, is linear. Okay? Letter C. This is actually the last question for this lesson. In the space below, do you see there's a space for a graph, a table, and an equation? I would like you to make two relations that are linear functions. So out of these three, you need to make two of them linear and one that is non-linear. So out of these three, you make two that are linear, one that is non-linear. Okay, it says one must be a graph, one must be a table, one must be an equation. So out of these three, make one of these non-linear, the other two linear. Go ahead and pause the video and try this right now. When you're ready to continue, hit play, and we'll go through it together. Now, out of these three, I'm actually going to do both. Okay, I'm going to do blue is linear, and I'm going to do red is non-linear. So if you did a non-linear graph, all you have to do is draw something that's not a straight line. Now, there is a caveat here. If you did this, that is not a non-linear function because that is not a function. Remember that vertical line test? It would fail the vertical line test at 1, 2, 3, 4, 5 different places. So you actually have to be a little bit more cautious than that. This is a non-linear function. This is a linear function. Okay, so straight line or curvy line, linear versus nonlinear. I'm going to go to the equation. Linear function, make something in slope-intercept form, 3x minus 2. That's a linear function. A nonlinear function, y equals, add an exponent. We saw that's one of the things that makes something non-linear. So y equals 1 half x to the 4th minus 8. Or, another one that's kind of funky, y equals 3 over x plus 2. This is not something we've really seen before, but I wanted to show you this. If you have an x in the denominator of your fraction, that will also be nonlinear. Boom, boom, we don't need you, let's go. Y equals 3 over x. Look at it already. Look at it. That's a big old curvy weird thing. Plus 2. All the plus 2 does is it just raises the function up a little bit. It changes the y-intercept. All right, but check that out. Nonlinear. Because this function cannot be written in slope-intercept form. There's no way to get this x back up to the top to make it like normal slope-intercept form. Okay, non-linear. Now, the table's the one that takes probably the most work to get right. In fact, I'm gonna linear, and I'm gonna go like this. And then the other one, I'm gonna make this non-linear because I'm trying to do everything for you. You didn't have to do this. And then line down the middle. Good enough. All right. Now, nonlinear function, I would do something like this. 0, whoa. 0, 1, 2, 3, 4. And then for the y values, I would just make a bunch of random numbers. 9, negative 2, 14, 13, 6.4. The chances of the slope being the same everywhere here is very, 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 very small. That would be a nonlinear function where they don't follow a pattern. Where by contrast, a linear function follows a pattern. 0, 1, 2, 3, 4. How about 8, 7, how about 8, 10, 12, 14, 16. I'm just going up by 2 each time. Linear functions follow a pattern. Nonlinear functions don't follow a nice consistent pattern. Okay, so I did both linear and nonlinear for each. You only had to do one nonlinear and two that are linear. But I wanted to show you different varieties of things you could have said. And that's it. Summary. How can you tell by looking at a graph if a function is linear or non-linear? I'm not even going to tell you to pause the video. Just, you know the answer already. If the thing's curvy or not. If you're looking at a curvy function, like, well, here, if you're looking at a curvy dude, he's non-linear. If you're looking at a straight line, that's linear. Graph, non-linear. Graph, linear, straight line. Graph, non-linear, curvy. So you can tell by looking at the graph if it's linear or not. By looking at an equation, you're looking for exponents or if you can write it in slope-intercept form. From a table, you're looking to see if the slope is the same everywhere. If the slope is the same everywhere, it's linear. If your slope is ever different, it is non-linear. Thank you so much for watching this lesson on the difference between linear and non-linear functions. Until next time, toodles.